So thank you very much. And without further ado, I would like now to give the stage to Daniel Worrall, who's a very distinguished researcher in deep learning and geometric deep learning, has done marvelous work in the past, and I hope he is going to enlighten us about geometric deep learning and the recent developments.
Well, thank you very much, Max. That's extraordinary introduction. I think distinguished is probably a bit above my pay grade at the moment, but I will happily go for that today. Okay, so I hope everyone can see my screen, and I'm just going to minimize a couple of things and set my pointer to laser pointer. And yeah, well, let's. Oh, I don't seem to have a clock here, so if someone could just tell me, say 10 minutes before the end, that the time is coming up, that would be very useful, please. Okay, so let's start. So I'm going to be talking about equivariance, which is a sub community within the geometric deep learning community. And instead of sort of going through a specific example of a paper today, we thought it would be better to talk about the general trends and challenges in this field. I'd just like to highlight that I am employed by Qualcomm, which is one of the sponsors of the ELIS program. Okay, so the agenda today is I'm going to be talking about why are symmetries important, especially in the medical imaging field, and then I'm going to review some of the basics for about 10 minutes, and then I'm going to dedicate about another 10 minutes to trends, or maybe 15 minutes, and another portion to challenges which are as yet unsolved, or maybe have some solutions, but which beg a lot more research. So this is supposed to be, it's designed to be an overview. You're not supposed to get everything on the first pass. By all means, revisit this, but it's just to sort of let you know what people are interested in and what people want to do research in the future. Maybe it will give you a good idea of what to research in the future if you're interested in this area. Okay, so symmetries abound in medical imaging tasks. So just take this very simple example where I've got a little circular disk of histopathology image, and I want to do some kind of boundary segmentation task. And maybe my algorithm gives me this sort of output here on the right. Now, a very obvious behavior of an algorithm or model that we would build is that if I do something like deform or rotate my input image, and so this is rotated by about 45 degrees here, then we would expect in common sense terms that our segmentation would also rotate by that amount. And this property is called equivariance. And the little diagram I've drawn here is called a commutative diagram. And this might seem like a very intuitive property that we want our models to have, but in general, a priori, these models aren't built with this sort of inductive bias already. So the field of symmetry, or field of equivariance, I should say, is about building this particular bias into networks. And this isn't a contrived example. You can look across multiple medical imaging sort of subdomains, such as detection, segmentation, reconstruction, and denoising, and they all have some sort of requirement based on symmetry, which you can see. And so it would make sense that models which have this property would find a good home in the medical imaging world, and not just medical imaging world, in many other worlds, but medical imaging in particular, because of the nature of this workshop today. And symmetry isn't just some sort of nice property. There are actually very good reasons why we want it, namely reliability and safety, reproducibility, and accuracy. Unlike people who build cat detectors over in big American tech companies, internet tech companies, who are just interested in sort of raw accuracy, we're very much of the time interested in other things in the medical imaging domain, such as reproducibility or reliability. If I take a medical image and deform it or rotate it slightly, I'm never going to pass an FDA test if my output just completely changes depending on input orientation. So this is a property or a metric which we're really, really interested in. And being able to give actual hard guarantees that models have this particular property is actually crucial for the safety of a lot of the products which we will be eventually pushing into hospitals or markets around the world. There is also one other property, which is sample efficiency. Maybe it should be separated from these three, but it's actually been shown in a number of works. I'm going to show this in a few slides, that these models actually, because you have injected so much extra domain knowledge about the way how this task should perform, you actually need a lot less data to train. And this is actually ideally suited to the medical imaging arena, where a lot of the time, unless you work in histopathology, but a lot of the time we have very scarce data. So this is sort of a quick overview of why we would like to do equivariant deep learning and medical imaging. Just as sort of an overview of what people have been doing in the last couple of years, you may also just want to get into it because other people are. Not always a good idea, but I think it's evident that this is definitely a very interesting area, and it's definitely an interesting area from the point of view of Google Ngram search. So group convolution, I'm going to cover this in a bit. It's sort of the workhorse basically of equivariant deep learning. And since 2016, this is when a student, Taco Cohen of Max Welling, published a paper. After that, we've seen a huge explosion in the number of people basically publishing stuff with group convolution in the title. And although correlation and causation aren't really to be matched, I would assume that the underlying cause is something to do with Taco's paper. And it's not just in sort of the general sort of world of the internet. This is also the case in our little corner of medical imaging as well. I've just highlighted 6 papers here, but there are plenty more where people are starting to apply these techniques to medical imaging related problems. You see here medical image analysis, histopathology, pulmonary node detection, segmentation. There's lots of different sort of interests in this work. So let's just look at a particular example, because I said something about sample efficiency earlier. Sometimes I talk to people and they think, oh, these models are maybe a bit of a theoretical fancy, because there's a lot of mathematics in these papers and they do seem quite theoretical. And as of yet, no one's actually applied these, I don't think, to the ImageNet competition. But why that is, I don't actually know at the moment, but I think there's some very good sort of indications that these models are very powerful already. So there's this paper by Erik Beckers, who's actually an assistant professor at the University of Amsterdam, currently, called Roto Translation Covariance. Covariance, another name for equivariant. Convolutional networks for medical image analysis. And in this paper, what Erik did and his collaborators was to try these sorts of networks, these symmetric networks on a variety of medical imaging related tasks. So mitosis detection, vessel segmentation, cell boundary segmentation. And what he's done is he's plotted in graphs, essentially he's compared various different kinds of networks with different levels of symmetry embedded or baked into them. And so you see along the bottom here, number n, and n basically stands for the number of symmetries you consider. And in this case, it's rotations plus translations. So n equals 4 means we're going to build a network which is symmetric to 4-fold symmetry. So these are 90-degree symmetries of rotation of our input. Or n equals 16, it's going to be 16. That's 22.5 degree rotations. And along the vertical axis, he plots a performance metric. Higher is better. And he shows that with increasing amounts of symmetry in general, we get better performance. This one's a bit interesting here, but in general, we get better performance. And what he's also done is he's compared these models where he's actually trained them without data augmentation against a CNN baseline trained with augmentation. And what he finds is that the equivariant networks in some cases outperform the basic CNNs with data augmentation. And so this is just to clarify that the accuracy of these models is, or the performance of these models is on par or sometimes better than underlying CNNs plus data augmentation, which is always quite an interesting thing, because people will usually think, well, why not just do data augmentation? And on top of that, we actually have a guarantee that these are going to perform well, at least on these 8 or 16 rotations. We're going to get the exact same result every time. So I think this is a very motivating, at least I think it's motivating, which is why I put it in the talk. But I think it's a very motivating reason for why we want to use these models in the in the medical deep learning world, or any kind of equivariant processing. Okay, so if you don't know what equivariance is, I'm going to give you just a very brief overview now, and I hope it's understandable to most people. I think it will be, but it's going to be very brief. And there's going to be plenty of pointers to papers in this talk, and yeah, so you guys can always find relevant pointers to relevant literature. So equivariance is a kind of what we call an inductive bias, a kind of a hard prior. And in the statistics world, we have a spectrum of models with different levels of priors, which we have. And the two ends of the spectrum, which aren't really realizable, but which are ideals in some case, are on one side, we've got these white box models. These are basically the pure sort of theoretical analytical models which you could think of, which have no bearing with reality whatsoever, and they're just completely uninformed by data. These are just like physics models in some sense are like this. They're very philosophical objects. There's nothing to learn here. On the other hand, we have black box models, which are basically purely empirical models which just learn 100% from data. There are no assumptions whatsoever embedded in these. Now, the reality is there is no such thing as a white box model, and there's no such thing as a black box model, because these are really just ends of the spectrum. And in reality, we have what we call gray box models. And most machine learning models, or actually all machine learning models, I should say, sit here. So regression is an example where you have human choices such as polynomial order, likelihood, or prior distribution choice. These are white box choices, but there's also learnable parameters within there, which are black box choices. And with deep learning, people talk about universal approximators all the time, but actually the models we work with on a daily basis are not universal approximators. They don't have an infinite number of hidden units, and we have all sorts of parameters such as number of layers, nonlinearities, optimizer choice, convolutional structure, or no convolutional structure, which actually are very important design choices which affect the performance of your network. So the whole field of machine learning, in some senses, some might say, would be about choosing which inductive biases to put into certain models and which not. And then once you have those, how do you deal with those? And the field of equivariance concerns itself primarily with convolutions. And we're going to go from convolutions to symmetry and what the connection is in the next few slides. So this sort of stream of work began in 2016 by looking at properties of convolutions and trying to generalize them. So convolutions use this, they're basically linear layers with two properties, which are translational weight tying. So neurons, which is translated separated by translation, share the same weights, and also with small receptive fields. And this gives us a convolution. But it is really just a linear layer at the end of the day with a couple of constraints. And so you might think of a layer. There's multiple ways of defining a layer, but layers usually, for me, they have some sort of linear component plus an affine plus a bias, and then there's a nonlinearity. They generally come in this sort of form, and we're just replacing the linear part with a restricted linear operation, which is a convolution. And mathematically, this will be useful for later. These convolutions, they are basically, you can just write them like this, as a collection of inner products between some feature map and a set of translated filters, where the translation is indexed by this parameter x. And these have been in use since Jan LeCun made the CNN back in the 90s, or maybe a bit earlier than that. But the convolution itself has been around much, much longer. For the nitpickers out there, yes, this is actually a cross-correlation convolution, but for some reason, by a nomenclature mishap, probably we call it a convolution. So this is different from the convolution found in the signal processing literature. It's actually the cross correlation, but we call it convolutions in this field. Another way to view this operation here, we can always rewrite these using a vectorization procedure where we vectorize our feature maps F, and we can then sort of turn our W's into a matrix. And this really makes explicit that linear structure that we have. So we've got a linear operator, just a matrix multiplication. And you can see the locality and the weight tying very explicitly in this diagram here. Okay. So why exactly do we choose locality and weight tying? Well, the weight tying comes from a property of the task, which is translational invariance for, say, classification, or translational equivariance for segmentation. And the basic idea is it's so simple, it's kind of sometimes a bit insulting to say this, but these two images are both images of dogs. And the difference is the separation of the distance of the dog from the left-hand side of the image. And to a computer, these are completely different images. The pixel values are just different. But obviously to us, they're the same semantic content. So we have translational invariance of this task. And this is why we have this weight tying here. For the locality, this is actually not a property of the task, but of the data. And I want to emphasize this difference very much. It's a property of the data. And in natural images, I'm not so sure about medical images actually, which might indicate that CNNs are suboptimal. But at least for natural images, pixels which are further apart are less correlated. And this has been well studied with, say, the work of Jan Koenderink and others many, many years ago. So these two weight tying and locality properties essentially mean that we have very few learnable properties, learnable parameters in these W's here, which means we're very parameter efficient, which implies that we're also, hopefully, very statistically efficient, provided we do our weight tying correctly. And with the advent of GPUs, in the last 10 years in deep learning, makes us very computationally efficient through parallelization. And the whole mantra is, why build translational weight tying into networks? Why learn it, when we could just build it in? And you could just take that basic maxim to its extreme and say, well, why build rotational, scaling, warp, shear, color, jitter, blur, weight tying in when we could just build it in? People haven't done this stuff in a built-in form, but people are doing it in the equivariance world. And usually people have attacked this with data augmentation, but I think equivariance is chipping away at this. Okay, so just a quick mathematical, just to make some things a bit more solid mathematically, then we'll go on to trends. So a function is invariant to a set of transformations if it satisfies this this equation here, where I is going to be your input image and T is your transformation operator. And you can see definitely here that symmetry is a property of these functions, of the task essentially, not of the data. It doesn't speak about I, it speaks about F. And these transformation operators could be anything: translation, rotation, data whitening. There are actually some properties which these must obey, but there's a bit more advanced than this talk. And so, yeah, there's lots of properties which embody invariance, classification, signal discovery and detection. This has lots of nuisance orientations. Dynamical systems, I'll touch upon that later. The form of their equations are invariant to certain transformations. And even the cocktail party problem of disentangling, this is actually an invariant problem. When you separate overlaid conversations into n separate streams, the ordering of the streams doesn't affect whether you've disentangled properly. So you have permutation invariance. Equivariance is this property where we now say, okay, corresponding to this input transformation, there's going to be an output transformation in the feature space. So invariance is a special class of equivariance where the output operator is just the identity, and the convolution, surprise, surprise, is an equivariant operator. So basically, translations of my input images lead to translations of my feature maps. And yeah, you can build these commutative diagrams again, where I've got, pictures of dogs or whatever, and I rotate them, and there should always be a closure of this commutative diagram in the feature space. Now, the interesting and very important point actually comes in a form of a theorem which has been improved upon by 3 different people, Condor and Trivedi, first in 2018, and then Cohen et al. In 2020 last year, and Becker's last year, which is that the group convolution, which is a generalization of a convolution, is the only linear map equivariant to group structured transformations. So I'm going to dive into what exactly the group convolution is next, and we will then see ways or problems which arise from this convolution and what people have been doing to build this to different groups or to groups of certain structures or properties which are difficult to handle. So this is our convolution, which we're used to, and the basic thing to do, the simplest thing to do, which also seems to work extremely well, is just to change this translation operation into a general transformation operator here. So instead of translating my kernel, what I'm going to do is I'm going to rotate it or scale it or flip it or something like that. And this actually preserves all of those wonderful equivariance properties. So if I then rotate my image, there will be a corresponding transformation in the feature space corresponding to this transformational rotation or scaling or whatever of f. Proving this is actually quite simple. It's quite nice, very satisfying. And this is basically the main thing which people are using at the moment, and basically lots of papers just sort of riffing on this in different ways. So yeah, we've got a transformation operator here. We have to adjust the domain, usually in deeper levels of our network. And X has this wonderful new interpretation of being a parameter of the transformation now, which I've always found a very satisfying interpretation. Okay, so there are many other flavors that exist, and well, I'm going to step you through some of them just now. Okay, so trends, this is by no means a definitive and complete, exhaustive collection of papers, and I apologize if I haven't included one of your papers in here, but this is some of the things which have got my attention in recent years. It's only been 5 years and a lot of work has happened. So one of the trends is basically to try and build this group convolution, which I've just got here again, for all the groups you can possibly think of which occur in our tasks. Basically, the way how it's gone over the years is, another group, another paper. I'm guilty of this. I've caught me red-handed. But actually, I think this is not, to be less cynical, I think it's actually a very good demonstration that this very theoretical, abstract quantity here is useful. And it's a good empirical exercise, and I think it's a good demonstration of a scientific process that we are able to, across many domains and many different examples of groups, show that the performance of these things works very well. And yeah, consistent results, basically the main take home is that we have improved sample complexity especially for small data sets, but that's basically the area where you're going to get most of your improvements. Obviously, you have a lot of data, do the sort of the OpenAI thing, or Google thing, get a lot of data, you're always probably going to do quite well. And you don't need so many inductive biases. But knowing exactly how much data is enough data is always a difficult question to address. And especially in this domain, I think it makes a lot of sense to use these models. By the way, just in case I just remembered, people don't know what a group is. Well, I'm going to just skip what the definition is, but a group is just an abstract formulation summarizing the structure of transformations. So it's just the way which abstracts the structure of, say, a rotation from the actual way how we implement it. And these groups, they can be associated with lots of different kinds of transformations. So people have been working on 2D and 3D convolutions for a long time, but people have been building these convolutions to be symmetric to different kinds of discrete rotation groups. So n-fold 2D rotations, the cyclic group of order n, 4-fold 3D, so it's the Klein-Sphere-Gruppe, 12-fold 3D, the tetrahedral group, the cube group, 24-fold, continuous rotations. So you can actually make these things to be equivariant to continuous rotations in 2Ds. I had a paper called Harmonic Networks in, I can't remember, 2017 maybe. 3D, there's a lot of work on 3D. The structure of SO3 is very complicated to deal with. So this is a nice area. Reflections and scaling sort of different ways, continuous, discrete scaling, stellations only. And you can combine all of these in different ways, and then you can, if you get translation plus rotation, then you get the special Euclidean groups. Add in the reflections, you get the orthogonal groups. There's a lot of work in here, and people in the physics literature have taken these to all sorts of exotic things like Lorentz groups, you name it. So this is a big area. And okay, so now onto another area. So this is really going to be just a random smattering. Generalizations. So I put it, tongue in cheek. Your paper is just a special case of my paper. I hope people understand this as a joke, and I think hopefully people identify with this as well. So I'm going to start off with an example of a paper written by a master student of mine, Nikita Diaconou, and myself on unitary convolutions some while ago. And so it's basically just relaxing constraints given by this kind of convolution. So here we have what's called a direct representation. Basically, we can only transform W by indexing points in its domain. And this doesn't allow for interpolation at all. And if you want to do interpolation, which I'm going to denote by putting the transformation operator outside W, then it turns out it breaks convolutional equivariance unless it turns out that this transformation operator is unitary under this inner product. What that means basically is for different interpolation settings, and I've got 3x3 input here being rotated on the nearest neighbors or bilinear interpolation. What it means is that the norm of your underlying signal must be invariant under transformations here. And the norm in this case is going to be the L2 norm. So basically it says the energy of the image shouldn't change when I rotate in some interpolation scheme. So that was one area. So being able to work with interpolation was very important. And then another completely different area is gauge symmetries. So these sorts of transformations that we model are what we call active transformations. If I take an image and I rotate it, that is an active transformation. But there's an alternative description of transformations, which is a passive description where you take your coordinate frame and rotate that. And then the coordinates of your vectors describing your objects will change. And so this is one change that you can consider. And there's also a second one, which is to move from global symmetries to local symmetries. So now if I have not a single coordinate frame, but if I have a coordinate frame at every single point in my manifold, or my space, then gauge symmetries are essentially the symmetries of coordinate frames under all of these transformations per point. And Maurice Weiler and et al. Basically came up with a riff on the group convolution, actually a generalization of it, which enables us to work with these gauge symmetries. And here it's written in a continuous form, but you could just replace the integral with a sum, and it looks fairly similar. And they found that you need to have a correction term motivated by the curvature of your space, actually, which will correct the values of f or w to perform this integral here. Another area where people have been generalizing is basically, it turns out that groups are very, very restrictive. You have to have inverse operations in your set of transformations. So you should always be able to invert, say, a scaling operation or a rotation operation. That's not true of all transformations. For instance, digital scalings. And it turns out that you can basically make something which is equivariant to non-invertible transformations by moving your transformation operator from your weights to your feature maps. It's really, really simple. But yeah, this guarantees your equivariance. So this is another area people be looking at to different axioms of your groups and definitions and changing those. So you can build equivariance to scalings. And so, for instance, there's a work which I did some years ago, which connects the group convolution actually with scale spaces, and that was called deep scale spaces. So there's a very nice connection there. Another area where people have been looking into is different kinds of problems. So there's these problems in RL where, say, I have this inverted pendulum, and I want to form a policy to keep it from falling downwards. And I could imagine if I flip my pendulum, that my policy is going to also flip in some corresponding manner. And so this shouts out equivariance. And it turns out that Elisa van der Pol was able to show that there's this area of MDP homomorphisms which imply in the area of RL that equivariant networks are needed. Another generalization can be found in this literature here, which is super interesting. I'm trying to understand it, but it's RL is not my thing, but it's a very, very fruitful area of research from about 20 years ago. Other areas where people have been looking into, and you're going to hear a bit about this next, I think, in Yalma's talk, is the work on meshes and on spatial graph convolutions. And I think there's been a lot more work in this graph convolution literature on invariance and equivariance, partially because there's no discretization artifacts that you have to worry about. And there's two main approaches which have been taken to building convolutions on graphs. Well, three actually, but I'm going to mention two. In the spatial domain, this is to consider what happens if I permute all of the nodes in my graph, if I permute the labels of my nodes. If I want my features also to permute, then there's this wonderful work by Hagai Moron et al., which shows you exactly what kind of linear layers you can use in place of a convolution, which do the exact same thing. And he finds some sort of really remarkable results. He's able to build spaces, linear subspaces of linear convolutional layers, which are perfectly equivariant. A refinement of this work, which was in some sense groundbreaking, was done by Pim de Haan, which is also a wonderful piece of work. He's also here at Qualcomm, as you can see, called natural graph networks, where instead of considering permutations of nodes, what they do is they look for permutations of neighborhoods. So what you say is that neighborhoods with the exact same connectivity structure should have the same functional mapping. And this is, in a way, a form of generalized weight tying, but across structurally similar neighborhoods. And so this is a very interesting paper to read as well. Another area that people are interested in is in choosing your representation which you use. So what do I mean by that? Well, we build networks from cascades of linear layers and nonlinearities, and choosing the form of this transformation operator deep within your neural network is not obvious. You can imagine just taking your F, your feature vector, and vectorizing it, and then decide, S is going to be some linear operator. And this is what's called it's a bit confusing. It's also called a representation in group theory. It's a very theoretically motivated name. It's not the same as a machine learning representation, which refers to the vector itself. That's a confusion sometimes. But there are multiple choices for what S could be. So just take 2D rotations. I could choose complex numbers. I could choose 2D rotation matrices. I could just choose this kind of operator, which just shifts my signal along a circle. And all of these representations, all of these things actually model the same underlying thing, which is a 2D rotation. They all have the same structure of a rotation. but it's not obvious which one's the best. And there's some connections with Fourier transforms, but Gabriele Chaser and Maurice Weiler recently had a paper, or actually not so recently, over a year ago now, where they compared lots of different choices of representation inside a network. And they found that this one here, this regular representation, which is used in the group convolution, is the best. And all of these other flavors of equivariant convolution that you can get from choosing different kinds of transformation operator don't work as well. And there's a big question mark over this. Like, why is that the case? I don't know. I've got my suspicions, but I don't think many people know yet. So if you could crack this why question, that would be very useful. Another area which people are interested in, there's quite a lot of these actually, is nonlinear equivariance. So people have been building equivariance to convolutions or equivariance to linear layers, linear equivariance, but nonlinear is really difficult because it's just such a huge space of nonlinear functions that we could work with, and it's not obvious how we do that. So there's two papers, one by David Ramiro and another one by Fabian Fuchs et al. I'm on that as well, where we've been looking into building equivariant attention, because attention itself is a nonlinear function. And attention, if you know it, is essentially, it can be written like this. It's just a weighted sum of features where the attention weights, these weights, are dynamically allocated per instance. And so the solution that most people have come up with so far is just to make this attention weight invariant to certain transformations and this V equivariant. But there are plenty more ways how this could be made equivariant, which have just not been explored. And I think this is a huge area, which is a lot of work to uncover.
Danielle?
Okay.
You've only left
Yes?
minutes.
10 minutes. Thank you. Okay. Perfect. I'm on time.
Actually, I'm not sure because we started late. So I think we started late. So I think you can certainly take some more time. You have 15 minutes plus 7 minutes, so don't worry.
Yeah. Okay. So 10 minutes would be perfect there because it would mean I'm just on time. Thank you very much. Okay. And then another area, which is going to round off my trends, is what I call, these aren't the actual name, but what I call tangent space convolution. So this is how do you do a convolution on a curved manifold, on a curved surface. And the general idea is you could imagine doing a convolution on the curved space, and curved spaces might be, say, a Lie group itself, but you could also just think of like the surface of some of a graph which represents, I don't know, some vessel segmentation or something. Instead of doing the convolution on the space itself, what people have been doing is they've actually taken a tangent space. So you take the tangent space at every point, and then you map your data from the manifold into the tangent space, and then you do your convolution in that space. And this has been done by gauge equivariant networks, but also more recent work by Eric Beckers, again, on B-spline networks, or Mark Finzi on LeComs has been doing this. And they always have this sort of form where you have some mapping into the tangent space, some correction for doing that logarithmic map, that map into tangent space, and then performing a convolution there. And I think this is a very interesting and very natural idea. It's very elegant as well. And then what you can basically say is we're going to do weight tying. In this case, will correspond to tying the weights of my kernels across all tangent spaces. So that's a very nice result. Okay, so that was some of the trends. There's quite a lot of them. And now I'm going to go to, I think, 4 or 5 different unsolved problems which a lot of people have been talking about or have alluded to in papers, what I call the frontier. So one big one is this mismatch between continuous transformations that we work with and the discrete data that we are given. We always have pixelized or voxelized or graphed data, but this data might all exist in a continuous world. And how we deal with that is with discrete processing is very difficult. So there are 2 main approaches that people have used. One which is to basically to discretize your transformations very, very finely. And so here on the right, you see an example of a vessel. And what I've done is I've taken the inner product between different rotations of this sort of elongated filter here, and the input. I've taken inner products, and you see the results, the responses along the vertical axis. And by doing this, essentially, for every extra discretization that we involve, we're going to add another level of processing that we need to do. So this is actually a very expensive thing to do. If we discretize a group, 100-fold, then we need 100 times more processing, roughly. And this is really expensive, but it actually gives us very good performance, as Gabriele Chesa and Maurice Weiler found in their survey, which I talked about earlier. But it is inexact, because between discretization points, you don't have any guarantees. The alternative is to use these things called steerable convolutions. They're built on these irreducible representations of groups. It's a different flavor. I haven't talked about them so much, although they popped up now and again behind the scenes in what I've presented. These kind of networks are highly constrained to be exactly equivariant across your transformations, and they're very difficult to work with, and the performance is not as good as these finely discretized groups. So why is it that breaking equivariance and discretizing finely works better than just being exact? It seems that being exact but using highly constrained kinds of filters doesn't work so well. So this is a question which a lot of us have been asking. I mentioned it earlier, why we don't know at the moment. And maybe there's a third way. I don't know what it is. People would be very interested if this were to come out in literature. That would be super interesting. Actually, there is a third way. I'm going to mention it in a moment, but I'm not sure if it's the answer just as yet. Another area, and this is actually related to the third way, is dealing with very, very large groups, also known as non-compact groups. So these are infinite groups, but infinite in a way which makes them very difficult to deal with. Viewed as in a mathematical sense, viewed as a topological space, these groups are not compact, they're non-compact. So things like scaling, shears, even affine transformations, you can keep on scaling ad infinitum, essentially. And that's an example of what we mean. You can just keep on scaling. You can always scale. So if I were to build a convolution where I build it over multiple scalings of my input filters, and those scales go on forever, my integral or my sum is going to be infinite, and I can't do that. So people who deal with infinite integrals a lot of the time are people who work in the Monte Carlo world, actually. And Mark Finzi, with his LeConf paper, attacked this by essentially, this is just a continuous version of the sum, essentially, but this is under the hood just a group convolution. What he's basically done is he's Monte Carlo sampled this, and it seems to work very well, actually. But whether this is the be-all and end-all of it, I'm not quite sure. I think there's a lot more work or research which has to be done towards this non-compact problem. Are there other ways to approximate this integral? By the way, I said there was a third way earlier. This is you see we've got an integral here, which is over continuous space. So this is actually a way to build convolutions over a continuous space. But because we're doing Monte Carlo sampling, we can do it with finite sums. So this is an idea which people have been thinking about, and it's nice to see that someone's actually gone and done it. But whether this is the future, who knows? But I would say watch this space. Two more things just to finish. One is computational complexity. I keep on coming up to it. With every new symmetry, we have a new dimension of compute. So we have a curse of dimensionality. And do we wait for the compute to arrive, or do we build more efficient convolutions? This is a big question to ask. Rich Sutton's bitter lesson, he basically says, wait a year and there will be a lot more compute. Maybe these models, just like we had to wait for GPUs to make CNNs work, maybe these models are just a bit before their time, like hardware-wise. But I think as environmentally conscientious researchers, we would want to work with more efficient versions of convolutions. And one last thing, or maybe actually, sorry, there's two more things actually. Sorry about that. One is projections. So this is another idea entirely which I've seen in the literature. And the idea is as follows, that we have lots of symmetries in the real world, but they get lost during data collection. Think about taking an X-ray. You've got 3D symmetries, which are lost when you project onto an X-ray using your radon transform. And so could we use these initial symmetries, which were then lost, as a good prior when we want to do things like reconstruction? And actually, there's a paper I should have included in here by Carlos Esteves and et al. Over at Pennsylvania, who had a good way of doing this as well. But there's also a DeepMind paper which has done something along these lines, where they have used 3D transformation priors when they want to do 3D reconstruction from 2D images. But it's not so much research, and I would be interested to see if more explicit equivariant processing would help. And the very last question for the future, the last frontier, is unsupervised symmetry learning. Maybe not so much to do with medical imaging, but I think just a very interesting area. Nonetheless, I call it a golden egg in the area. Solve this and you've solved some very, very long-standing questions. And one work I've seen already on this is Hamiltonian generative networks. I actually spoke with Danilo Rezende about this, and apparently Hamiltonian generative networks are okay, but in general, this is a really hard problem, and this is not the be-all and end-all of it. So if you could learn symmetries of dynamical systems, I should say, because you always have to have a task to be invariant to, then solving this problem would be very, very fruitful indeed. It would allow you to do automated science in some sense, because a lot of, say, modern day physics is written in the language of symmetries. Yeah, so I think I am just on time, hopefully. And I just want to round up by just sort of saying the things that I covered today. So I covered a lot of trends, I covered a lot of frontiers. The trends were to look at different groups, generalizations of convolutions, working on different domains like graphs or on manifolds. Then there's also problems with representations and nonlinear generalizations of the group equivariant convolution. And some of the problems which are just really unsolved at the moment, I'd say, are working in this continuous domain, non-compactness, complexity, and more esoteric things like unsupervised learning of symmetries, and also symmetries which get lost in the data collection process. And I'd be happy to take any questions from here.
Thank you very much, Daniel, for a super stimulating talk. That was very nice. Yeah, so if you have a question, you can raise your hand, and I see, or just type it in the Q&A box. Please do not type it into the chat box, because it will get lost in the sort of many other things which are being put there for between you. So if you have a question, put it in the Q&A box. I see one question there, but let me first give Jai the audience. So can you unmute and then ask the question? We can't hear you. Okay, so in the meantime, maybe somebody else can try to see if he can get unmuted. I'm going to read this question from Karan in the Q&A, which is, why is the n equals 8 higher than the n equals 16 in the leftmost graph? I think that was when you were talking about
Right.
Eric Becker's results.
This is a weird little phenomenon, and Eric was also quite confused about this, I think. don't entirely know. Well, actually, maybe I do. I think there is something else going on in this problem to do with the where was it? Yeah, here. I think it's something to do with if you have too much constraint. Maybe this problem isn't 100% rotationally equivariant, but I don't actually buy that. This is actually very confusing, I would have to say. I think there's another thing going on at play, which is learning dynamics. So we use these first order optimizers in this field quite a lot, and it might just be harder to train these models with more with fewer degrees of freedom. But yeah, if you could figure this out, that would also be very interesting. It's weird how it's only in this left plot and not in these others. So I'm not entirely sure about that myself.
All right.
It would require a lot of investigation.
Yeah, so if nobody else is raising their hand, maybe I can ask one question. So what do you think are the most promising applications of this technology that you see on the horizon?
I think in particular in the medical field, things like equivariant processing for things like segmentation, stuff like that. So maybe sort of more low-level tasks at the moment would be important, just so you can get very reliable results under all sorts of input transformations. And I think especially because there's very small amounts of data, that makes a lot of sense. So things like, as I mentioned, simple things like denoising, segmentation, reconstruction, nothing too fancy like labeling where a pulmonary nodule is or something like that, because I don't think we understand those particular processes deeply enough at the moment. Maybe we do. Maybe I'm not an expert on that particular subfield, but simple things like segmentation, reconstruction, yeah, that would make a lot of sense. And anything where people are already doing, it would make sense just to plug and play an equivariant version in there. Outside of the medical field, I think there's a lot of interest in places like physics or other areas where you have a very strong generative model of how the world works, because there you can really just look at your equations and you can identify what your symmetries are, or in other cases you can just say, okay, I don't know what the symmetries are, but I know that they exist, and so we might want to do some kind of discovery or something like that. I see a lot of potential in those fields. For things like, I don't know, like language, I don't see much of a use of these things at the moment. There might be at some point, but things where there's a lot of predefined structure, I definitely see a lot of potential. And these
All right, thank you.
these are very general blocks, aren't they?
So now lots of questions keep streaming in. Problem is we're running a little bit out of time. So I'm going to pick one and then maybe you can give a short answer and then we have to move to Jelmer's talk. So the top one says, you mentioned deformations at some point. Are there any works that allow arbitrary diffeomorphisms as symmetries?
Ooh, none which I showed. I guess there is some work from Andrea Vidaldi's group where they've been learning feature maps which are equivariant to subgroups of diffeomorphisms. Maybe not subgroups, but sort of subsets of diffeomorphisms, which is super interesting. I can't remember the name of the first author, but they're doing an unsupervised or semi-supervised learning. They sort of mix data augmentation and learning with equivariant features. It's an interesting area, but that's all I can think of.
All right. Well, thank you so much. And unfortunately, for the other people who have posted questions, I'm sorry, we are going to stop it here. I want to thank Daniel again for a wonderful talk. We can't really clap, but I'll clap for you and for the rest of the attendants. Attendees. So, so thank you again. And then we move to Jelmer,